All right, welcome back everyone to the deep dive. We spend a lot of time talking about the different machine learning models out there, but today we're going to sort of zoom out a little bit and think about the bigger picture of how we even get those models to perform well in the first place.
Yeah, absolutely. There's so much that goes on behind the scenes before you even get to see the results of a powerful AI. And honestly, it's something that people don't always appreciate. It's not just about picking a model and hitting go. It's a whole art and science to set up the training process just right.
You've sent over some really fascinating research that dives into exactly this. How to systematically figure out the best way to train these massive AI models that we're seeing more and more of.
Exactly. I think you'll find this paper pretty intriguing. It's called Optimizing ML Training with Metagradient Descent. And it introduces this really cool idea. Instead of just manually fiddling with all the settings and hoping for the best, they actually use a separate layer of optimization using something called metagradients to automatically find these better training configurations.
It's like an AI that helps train other AIs. Meta, right?
Totally, meta. And that's precisely what we're going to unpack in this deep dive, this concept of metagradient descent MGD. We'll break down how it works, the challenges that this research had to overcome, and some of the impressive results they were able to achieve. This could be a real game changer in how we approach training these increasingly complex models. So, yeah, get ready for some aha moments.
I'm ready. Let's start with the problem. Even if you're just starting out with machine learning, you quickly realize there are so many decisions to make even before you start training. It's not just about the model itself, it's about the data, it's about all these hyperparameters.
The data part is so huge. Just think about all the choices involved with the data. How do you clean it? How do you split it into training and testing sets? And when you have these massive data sets with potentially billions of examples, which ones do you actually use for training?
It's overwhelming.
Exactly. And the paper really drives this point home. They're saying that this traditional way of doing things, manually tweaking a few settings here and there, it's like we're exploring this tiny little corner of a vast universe of possible ways to train a model. There's this whole unexplored space of better training setups out there.
Like trying to find the perfect recipe, but you're only allowed to change the amount of salt you use. You're missing out on this whole world of ingredients and techniques.
Exactly that. So the challenge is clear. How do we explore this massive space of possibilities in a systematic and efficient way, especially with these giant models that are becoming the norm?
Okay, so enter this paper. Optimizing ML training with metagradient descent and their proposed solution. How do they tackle this beast?
So they have this really clever idea. They say, hey, instead of looking at this as a trial and error process, what if we reframe it as an optimization problem? Now, whenever we hear optimization in machine learning, what's the first tool that comes to mind?
It's got to be gradients. Gradient descent is like the bread and butter of how we train our models in the first place, right?
Right. So the big idea here is this. Can we apply the same powerful tool gradient descent, but instead of using it to optimize the model's parameters, we use it to optimize the training process itself?
Interesting. But you mentioned earlier that this idea of using gradients to optimize training isn't totally new. Like there's been some previous work in this area, right? So what's been holding it back from becoming more widely used?
Yeah, good point. The idea of using gradients to fine-tune the training process itself has been floating around for a while. The problem is that it just hasn't scaled well. Previous methods just couldn't handle the sheer size and complexity of the models and data sets we're dealing with now. They get bogged down, become computationally expensive, just not practical.
So that brings us to the central question this paper is trying to answer. Can we actually make this idea of gradient-based training optimization work at scale? Can we use it to train these massive models that are becoming increasingly common?
Yes, and they make a strong case for it. They've made two key contributions that really push this field forward. One of them is this new algorithm they call replay. It's specifically designed to efficiently calculate what they call metagradients. Basically, these gradients that tell us how to change our training setup to improve the final model.
Replay. All right, I'm intrigued. What's so special about it?
So replay uses this really clever trick. Instead of storing every single intermediate step during training, which would require a ton of memory, it recomputes some of those states on the fly. Imagine you're watching a really long movie and you want to understand a scene in the middle. Instead of recording every single frame, you could just remember a few key scenes, and then if you need to, you can sort of fast forward from the last key scene you remember to the point you want to understand.
So it's trading off a little bit of computation to rerun parts of the training in exchange for massive savings in memory.
Exactly, and this is what allows replay to calculate metagradients for much larger models than was previously possible. It's a game changer for bringing this whole idea of metagradient descent to a scale that's actually relevant for modern AI.
Okay, that's really cool. Now, you also mentioned this idea of non-smoothness in the optimization landscape. Even with replay, to efficiently calculate the metagradients, why isn't it just a straightforward matter of following the metagradient to a better training setup? What's the catch?
Ah, that's a great question. So it turns out that even with replay, just blindly following the metagradient doesn't always work as well as you'd hope. The researchers found that the landscape of this meta-optimization problem, the space of all possible training setups, can be very non-smooth.
Like a bumpy, rugged terrain rather than a nice, smooth valley.
Exactly. It's like if you're trying to find the lowest point in a landscape, you might think you're going downhill, but then suddenly there's this steep cliff or hidden crevice, and you end up getting stuck in a local minimum.
So the metagradient might be pointing you in a direction that looks promising, but then because of this non-smoothness, it actually leads you to a worse setup in the long run.
Exactly. And this is where their idea of metasmoothness comes in. They realized that in order to make metagradient descent really work well, they needed a way to design training routines that produce more well-behaved metagradients, gradients that you can actually trust to guide you towards better training setups.
How do you even begin to measure the smoothness of a training routine? And how do you make it smoother?
So it boils down to this. They're looking for training setups where small changes in the training configuration lead to predictable and consistent changes in how the model learns. So if you tweak a hyperparameter a little bit and the model's performance changes in a way that makes sense, then that's a good sign. It means the metagradient is probably pointing you in the right direction.
But if a tiny change in a hyperparameter causes the model's performance to jump all over the place, then the metagradient becomes unreliable.
Right. So to measure this, they came up with something called empirical metasmoothness. It's a more practical way to estimate how smooth the optimization landscape is around your current training setup. It basically looks at how consistent the metagradient's direction is within a small neighborhood of your current settings.
So a high empirical metasmoothness score means you can probably trust the metagradient to guide you towards better settings.
Exactly. And to actually improve the metasmoothness of standard training routines, they explored all sorts of modifications to common practices. They looked at things like the batch size, the width of the network, even the placement of batch normalization layers. And some of their findings were really surprising.
Like what? Did they find any tricks that seemed counterintuitive based on how we usually think about training models?
Yeah. For example, they found that placing batch normalization layers before the activation functions in the network instead of after, which is more common, could actually improve metasmoothness significantly. They also found that scaling down the output of the final layer could sometimes help a lot without hurting the accuracy too much. These are things that you wouldn't necessarily think of if you're just focused on getting the best performance right away, but they have a big impact on how well metagradient descent can optimize the training process in the long run.
That's fascinating. It's like there's this whole hidden layer of complexity to how we design these training setups. So we've got replay to efficiently calculate the metagradients and this metasmoothness framework to make those gradients more reliable. Now let's get to the really exciting part. What can you actually do with metagradient descent, or MGD?
The paper showcases some really compelling applications. One that really stood out to me was using MGD for data selection. They applied it to this competition called Data Comp Small, which is all about finding the best subset of data from a huge pool to pre-train a CLIP model. CLIP, for those who don't know, is this really powerful model that learns to understand relationships between images and text.
And choosing the right training data is especially crucial for these multimodal models, right?
Absolutely. If you're training a model to understand both images and text, you need to be really careful about what kind of data you feed it. And when you're dealing with data sets that have potentially billions of image-text pairs, just randomly picking some is not going to cut it.
So how do they use MGD to tackle this data selection problem?
Well, they framed it as an optimization problem, where the goal is to find the optimal data counts. So for each piece of data in the pool, they're trying to figure out how many times that piece of data should be used during training. Now, you can't directly use gradient descent on these counts because they're discrete numbers. You can't use half an image, right? So they came up with this clever workaround using continuous importance weights that represent how much emphasis to put on each data point. And these weights can be optimized using MGD.
So they start with some initial weights, and then MGD iteratively refines them to figure out which data points are most helpful for training the CLIP model.
Exactly. And the results were really impressive. Their MGD-based method achieved roughly double the performance improvement compared to the previous state-of-the-art for data selection in this competition. That's a huge leap forward.
That's amazing. It really shows the potential of MGD for automating this really crucial but often very time-consuming and tedious part of machine learning. And they didn't stop there. They also applied MGD to another important area, instruction tuning for language models. What's instruction tuning and how does MGD come into play there?
So instruction tuning is this process where you take a large language model, like one of these massive text-generating AIs, and you fine-tune it on a data set of instructions and desired responses. This is how you teach the model to actually follow instructions and perform specific tasks rather than just generating random text. And again, the choice of which instructions and examples you use for this fine-tuning process has a huge impact on how well the model performs.
So it's kind of like data selection, but for instructions instead of raw data.
Yeah, exactly. You have all these different data sets out there with instructions and examples, but which ones are the most effective for training your model to perform well on the specific tasks you care about? And again, MGD comes to the rescue. They were able to use MGD to select the best data from a collection of 4 different instruction tuning data sets and optimize the model's performance on these benchmark tasks.
And how did it compare to just using all the data or using other data selection methods?
It actually outperformed both. They used a Gemma 2B language model with this technique called LoRA for efficient fine-tuning, and MGD consistently found better subsets of instructions than the other methods. It's another great example of how versatile this approach is. It's not just limited to multimodal models or image data. It can be applied to a wide range of machine learning problems.
Really impressive. Now, one application that I found a bit surprising and maybe a little concerning was using MGD for these data poisoning attacks. What are data poisoning attacks and how is MGD relevant here?
So data poisoning is this malicious technique where someone tries to sneakily inject bad data into the training set to mess up the model's performance. You might think, well, if you just add a few random bad examples, the model should be able to ignore them, right? But it turns out that if you're clever about it, you can actually cause significant damage with just a small amount of carefully chosen bad data.
And MGD can be used to find this carefully chosen bad data.
Unfortunately, yes. The researchers showed that you can use MGD to actually frame this as an optimization problem. How can I change a small fraction of the training data to cause the biggest drop in the model's accuracy on a separate validation set? It's kind of scary to think about, but it also highlights the power of this technique. If you can understand and exploit the gradients of the entire training process, you can do some pretty powerful things, both good and bad.
Absolutely. It's like a double-edged sword. It's great that we can use it to optimize training and find better data, but it also means we need to be aware of these potential vulnerabilities and develop ways to protect against them. And speaking of optimization, the last application they explored was using MGD to find learning rate schedules. Why is that interesting, given that learning rates are a pretty well-studied hyperparameter?
It is interesting. While we have a pretty good understanding of how to set learning rates in general, finding the optimal schedule that is how the learning rate changes over time during training is still often a very manual and time-consuming process. People often rely on intuition and rules of thumb or just brute force, trying out a bunch of different schedules to see what works best. The researchers wanted to show that MGD can actually automate this process as well. They basically defined the learning rate as a function that changes over time and then used MGD to optimize the parameters of that function to minimize the error on a held-out validation set.
So instead of setting a fixed learning rate or manually tweaking it over time, MGD figures out the optimal way to change the learning rate throughout the training process.
Yes, exactly. And the results were quite impressive. The schedules found by MGD were actually competitive with schedules that were handcrafted by experts after lots of trial and error. It might not be the most practical application for MGD in its current form, but it really highlights the flexibility and potential of this approach.
I see. Even if you're not using MGD to directly optimize the learning rate schedule, it shows that you can use it for these really complex optimization problems that are hard to tackle with traditional methods.
Right. And the authors of the paper really emphasize that this is just the beginning. There's so much more we can do with MGD. They're basically saying, hey, we've shown that this approach works and it can achieve some really impressive results. Now let's see how far we can push it.
So what do you think? Where do you see this research going in the future? What are some of the big open questions and exciting possibilities?
Oh, there are so many. Like, how can we apply MGD to optimize even more aspects of the training process? Can we use it to automatically design better model architectures? Can we use it to discover entirely new training paradigms that we haven't even thought of yet? And then there are also the practical considerations. How do we make MGD even more efficient and scalable so we can apply it to even larger models and data sets?
It really feels like a paradigm shift in how we think about machine learning. Instead of just focusing on the models themselves, we're starting to think about the training process as this optimization problem that we can attack with these powerful mathematical tools.
Totally. And the potential implications are huge. If we can automate and optimize this training process, it could make AI development much faster, much more accessible, and it could lead to a whole new generation of even more powerful and capable AI systems.
It's an exciting time to be in this field, that's for sure. Well, this has been a fantastic deep dive into metagradient descent. If you're listening and you want to learn more, we'll be sure to link to the paper in the show notes. And if you have any thoughts or questions, feel free to reach out to us on social media.
Definitely. Always happy to chat.
Until next time.
See you then.